For half a century, one of the Milky Way's darkest predators has fascinated astronomers. Cygnus X-1, a black hole about 21 times the mass of the Sun, locked in a deadly partnership with a massive blue star. As it tears gas from its companion matter, spirals inward, heats to millions of degrees, flares in X-rays, and disappears beyond the event horizon. Tonight we explore what happens inside this extreme system, from the raging accretion disk to the warped space-time around the black hole itself. If you enjoy journeys into objects this intense, please subscribe and share, and tell us in the comments, what would you most want to know about a black hole that is actively devouring a star? Thank you for watching. Now let's begin. The Milky Way appears as a barred spiral galaxy, a rotating disk of stars, gas and dust wrapped around a central bulge with several winding spiral arms where new stars form in large groups. In this disk, stars orbit the center of the galaxy on paths that take hundreds of millions of years to complete, and the Sun follows one such path inside a minor spiral feature often called a local arm. When an observer looks toward the constellation Cygnus, the line of sight passes along this part of the spiral pattern through a broad stretch of the disk where the combined light of many stars builds a dense star field projected against the darkness of interstellar space. In that direction, the disk is seen almost edge-on, so the view passes through a long column of the Milky Way crossing regions near the solar neighborhood, as well as more distant segments where the spiral structure curves back toward the inner galaxy. Because the solar system lies embedded inside the disk rather than above it, astronomers cannot obtain a simple overhead view of the spiral pattern and instead must infer the arrangement of arms and interarm regions by combining distance measurements, stellar motions, and maps of gas emission along different lines of sight. Over time, this work has revealed that nearby spiral features form a complex pattern, with the local arm extending through the Cygnus region and connecting to larger arms that reach farther inward and outward, so that multiple concentrations of young stars overlap when seen in this particular direction. Along this path, interstellar space is not empty. It contains a mixture known as the interstellar medium, a combination of rarefied gas and fine dust grains spread through the disk. Some of this material is arranged in large clouds that are cold and dense enough to shield molecules from harsh radiation, and these clouds can collapse under their own gravity to form new generations of stars. Other regions contain warmer, more diffuse gas ionized by the ultraviolet light of hot massive stars, and these ionized zones can glow at visible wavelengths and radio wavelengths, outlining parts of the spiral arm structure against the background. In the sector of the Milky Way that lies behind the constellation Cygnus, there are large complexes of star formation, where many massive short-lived stars are born in close proximity. Groups of O-type and B-type stars, together with their lower mass neighbours, gather in loose associations that share a common motion around the galaxy and a similar age. Their combined radiation fields heat surrounding gas-carved cavities and create shells and filaments in the interstellar medium, while their stellar winds push material outward and can compress nearby clouds, possibly triggering further star formation. The density of objects along this line of sight makes the Cygnus region appear particularly rich in both stars and gas. Observations at radio wavelengths reveal emission from ionized hydrogen and from certain molecules that trace spiral arm segments and cloud surfaces, while X-ray and gamma-ray observations identify high-energy sources embedded within the same general area. The presence of dust grains mixed with the gas means that light from distant stars is partially absorbed and scattered, a process known as extinction, which dims and reddens their apparent colours compared with how they would look in the absence of intervening material. As a result, maps of the region must combine data from many wavelengths to reconstruct the three-dimensional distribution of stars and gas in this crowded part of the disk. Within the thicker midplane of the Milky Way, where the gas density is higher and star formation more active, Supernova explosions from massive stars inject energy into the surroundings, driving shock waves that travel through the interstellar medium. Over millions of years, these events, together with stellar winds and radiation, help stir and shape the galactic gas into bubbles, chimneys, and arcs that overlap and merge. The Cygnus sector of the disk shows evidence of such activity, with extended structures of hot gas and cavities, enclosed by cooler, denser shells indicating that previous generations of massive stars have already lived out their brief lifetimes. New stars continue to form within the remaining dense clouds, meaning that multiple generations of stars of different ages coexist within the same broad region of the galaxy. Against this background of ongoing star formation and feedback, the Milky Way disk maintains an overall thin structure on galactic scales about 1,000 light-years thick at the spiral arms, yet spanning tens of thousands of light-years in radius. Within this relatively thin layer, star-star clusters and star-forming complexes orbit the centre of the galaxy, with a range of speeds and eccentricities, while the spiral arms represent patterns of enhanced density rather than rigid physical structures. Above and below the midplane, the density of gas and young stars declines, and an older population of stars occupies a thicker component that gradually blends into the extended diffuse stellar halo. So most of the bright crowded features associated with recent star formation are confined close to the central plane that defines the visible band of the Milky Way on the sky. When the line of sight towards Cygnus is restricted to this plane, it intercepts numerous clusters, associations, and clouds located at different distances, which together create the impression of a single complex region, even though the individual structures may be separated by thousands of light years. Because different parts of the disk orbit at different angular speeds, these patterns slowly wind and change over long time scales, and the positions of arm segments relative to any given star drift over the lifetimes of stellar populations. The direction toward Cygnus therefore samples a long complex section of the disk, where the accumulated light of distant stars, the absorption by dust, and the emission from warm and hot gas together define the wider galactic environment in which individual high-energy systems are embedded. Star-forming complexes in the Cygnus region arise where large reservoirs of cold molecular gas gather in the Milky Way disk and become dense enough for gravity to overcome internal pressure. In these places, material that was once part of a more diffuse interstellar medium collects into giant molecular clouds that extend over tens to hundreds of light years, with clumps and filaments that reach even higher densities. Within such clouds, gas and dust shield the interior from most external ultraviolet radiation, allowing the temperature to remain low and the pressure modest despite the substantial amount of mass. Under these conditions, small perturbations can grow, and regions that are slightly denser than average can start to collapse. As they do, they fragment into cores that will become individual stars or multiple systems. The Cygnus sector contains several prominent examples of this process at different stages, where observers identify both cold clouds that are still assembling and active regions that are already rich in newly formed clusters. Some of the most massive cores in these clouds give rise to O-type and B-type stars, which are hot, bright, and short-lived. Their radiation output and stellar winds begin to alter the natal environment almost as soon as they form, carving out cavities and ionizing the surrounding hydrogen. The result is often an H2 region, a zone of ionized gas that emits characteristic spectral lines and can glow in visible and infrared light. Around the edges of such regions, cooled gas and dust can collect into arcs and ridges that trace the boundary between the hot interior and the colder exterior. In the broader Cygnus area, multiple H2 regions and associated star-forming complexes overlap along the line of sight, so that in projection they appear as a rich tapestry of emission and absorption structures. Within these complexes, young clusters of stars emerge as the embedded cores finish their collapse and clear away some of the remaining gas. Many of these clusters contain dozens to hundreds of stars, with a few very massive ones dominating the energy output. In associations linked to Cygnus, such as those identified through common motions and ages, massive stars are spread over large volumes, rather than confined in a single compact cluster. They share a similar origin in one or more giant molecular clouds and move together through the galaxy while they evolve. Because O-type stars live only a few million years before they exhaust the fuel in their cores and explode as supernovae, their presence indicates that star formation in these regions has occurred on relatively recent timescales in galactic terms. Surrounding each massive star, strong stellar winds flow outward at high speeds, carrying mass and momentum into the interstellar medium. These winds can merge and interact with each other, forming large-scale bubbles of hot, low-density gas that expand into the surrounding clouds. At their edges, the swept-up material forms shells and filaments that can be seen in various wavelengths, depending on their temperature and composition. Shock fronts driven by both winds and past supernova explosions compress some parts of the clouds and may help to trigger further rounds of star formation, while other parts are dispersed and thinned out. Over millions of years, this continuous input of energy gradually reshapes the region into a collection of cavities and dense remnants that record the history of feedback from successive generations of stars. Embedded within the larger complexes, there are also smaller, younger clusters still wrapped in their birth material. In these protostars continue to gain mass from accretion envelopes and disks, while jets and outflows on smaller scales carry away angular momentum and energy. Infrared observations are especially useful in these cases, because dust that is opaque at visible wavelengths can be more transparent in the infrared, allowing astronomers to trace the distributions of young stellar objects and the structure of their host clouds. Radio observations of molecules such as carbon monoxide complement this view by mapping the cold gas, revealing where dense clumps and filaments lie and how they move. Together, these datasets show that the Cygnus region is not a single uniform cloud, but a layered dynamic environment in which different groups of stars represent different episodes of formation. The stellar content of the association spans a wide range of masses. At the high end, the most massive stars strongly influence their surroundings through radiation and winds, while at the low end, numerous smaller stars form a long-lived background population that will persist for billions of years after the massive stars are gone. Intermediate mass stars occupy the middle of this distribution and contribute to the overall luminosity and enrichment of the galaxy as they evolve off the main sequence and pass through later stages. As time passes, clusters can lose members as stars drift away due to gravitational interactions or tidal effects from the galactic potential. Some clusters dissolve entirely, their stars blending into the general field, while others retain a bound core. Associations which are more diffuse from the outset gradually spread out along their orbits as small differences in velocity accumulate. In the Cygnus sector, this mixing process is still incomplete in many groups, so coherent patterns in position and motion remain visible. The gas dust and young stars that make up these complexes therefore trace both recent star formation and the longer-term evolution of material cycling through the Milky Way disk. In addition to their internal development, these complexes orbit within the gravitational field of the galaxy, moving through spiral arm regions where the density of gas and young stars is enhanced. As they travel, they can encounter other clouds or pass through patterns of density that slightly modify their structure and star formation activity. The combination of self-gravity feedback from young stars and the broader galactic potential means that each complex follows a unique evolutionary path, yet many share common physical processes. At any given time, observations of the Cygnus region capture a mixture of phases from cold clouds on the verge of collapse to matured associations whose most massive members are already shaping and clearing their surroundings. From the point of view of observatories near Earth, the direction of the constellation Cygnus defines a particular line through the Milky Way, along which radiation from many objects must travel before it reaches detectors. Light from the high-mass X-ray source known as Cygnus X-1 follows this path through interstellar space-crossing regions that differ in density, temperature, and composition. Along the way, gas and dust in the interstellar medium modify the signal in ways that depend on wavelength, so that the appearance of the source in visible light radio waves and X-rays is shaped by the material between the system and the solar system, as well as by the processes occurring in the system itself. Interstellar gas is present mainly as hydrogen and helium, with trace amounts of heavier elements. In some regions along the sightline, this gas is almost completely ionized and relatively hot, while in others it is neutral and cooler. Dust grains made of silicates, carbonaceous material, and ices are mixed with the gas and occupy a small fraction of the total mass, yet they have a strong effect on how light travels, because they are efficient at absorbing and scattering certain wavelengths. When visible light from distant stars or from a bright companion star near a compact object passes through such material, shorter wavelengths are typically scattered and absorbed more strongly than longer wavelengths. This produces extinction and reddening, making objects appear dimmer and redder than they would be in the absence of intervening dust. In the direction of Cygnus, the column of gas and dust is substantial, so optical observations must account for this effect to infer intrinsic luminosities and colours. In practice, astronomers model the distribution of interstellar extinction along the line of sight using observations of many stars at different distances, and then apply these models to correct the observed properties of sources embedded in this region. Distance measurements from parallax for nearer stars and from spectroscopic methods for more distant ones help to anchor these models on an absolute scale, so that the amount of dimming and reddening can be linked to the true space density of dust. At longer wavelengths, such as radio and some parts of the infrared, dust absorption is much weaker. Radio waves can pass through many of the same clouds that strongly attenuate visible light, allowing radio telescopes to detect emission from gas structures and compact sources that might be heavily obscured in optical bands. For lines of sight through the plane of the Milky Way, including the Cygnus direction radio surveys reveal numerous discrete sources, as well as diffuse emission from ionized and neutral gas. These data help map the spiral structure and provide independent measures of gas density and motion, which in turn improve estimates of the amount of material that X-rays must traverse. They also reveal that the gas is clumpy rather than uniform, with filament shells and bubbles on many scales that produce small variations in the column density from one narrow line of sight to another. X-rays interact with the interstellar medium in a different way. The atmosphere of Earth blocks X-rays almost completely, so observations in this band require detectors placed above the atmosphere on satellites or high-altitude instruments. Once in space, these detectors receive X-ray photons that have passed through the integrated column of gas and dust between the source and the solar system. Neutral atoms and ions in this material can absorb X-rays through photoelectric processes, especially at energies corresponding to the inner electron shells of abundant elements. As a result, the observed X-ray spectrum from a distant binary contains imprints of the intervening medium with lower energy photons more strongly suppressed than higher energy ones. By fitting models to the observed spectrum, astronomers can estimate the column density of hydrogen along the line of sight, which gives a measure of how much gas lies between Earth and the source. Dust grains can also scatter X-rays through small angles, creating diffuse halos of emission around bright point sources. The strength and angular profile of such a halo depend on the size distribution and composition of dust grains, as well as on their location along the path. Studies of X-ray scattering halos in the Cygnus direction therefore contribute to understanding both the interstellar medium and the distance and environment of individual high-energy sources. Timing information in X-rays is less affected by the intervening material because absorption and scattering processes at these scales do not typically smear out rapid variability by large amounts, although delayed scattered light can contribute a faint extended component. This means that changes in the X-ray brightness that occur near the compact object on timescales of seconds to days can often be detected with high fidelity despite the presence of gas and dust along the way. At the same time, variations in the intervening medium itself, such as density, changes in interstellar clouds or small-scale structure in the gas, can cause modest changes in the observed spectrum and absorption over longer timescales. Multi-wavelength observations combine these different perspectives along the same line of sight. Optical and ultraviolet data are used to characterize the visible companion star in a high-mass X-ray binary and to measure the amount of reddening it experiences. Radio observations probe outflows, ionized regions or interactions with the surrounding medium that extend beyond the immediate binary. Infrared surveys trace warm dust and cooler stars that share the general environment. X-ray and sometimes gamma-ray observations focus on the innermost hottest regions where matter releases large amounts of energy as it falls toward the compact object. By aligning these data sets on a common coordinate system and distance scale, researchers separate the effects of the interstellar medium from the intrinsic properties of the source. The path through interstellar space toward Cygnus X-1 is treated not only as an obstacle, but also as a measured component of the system, because its properties enter directly into any attempt to derive accurate physical parameters. Uncertainties in these corrections remain, but they can be quantified and included when derived quantities such as luminosity or mass accretion rate are reported. In the high-mass X-ray binary known as Cygnus X-1, the brightest ordinary source of light is a hot blue supergiant star that dominates the optical appearance of the system. This star is a massive evolved object that began its life with a mass many times that of the Sun and still retains a large fraction of that mass. Astronomers classify it as a late O-type or early B-type supergiant, a category that combines high surface temperature with a greatly expanded radius. Its outer layers are hot enough that the surface temperature reaches tens of thousands of degrees Celsius, so most of its radiation emerges in the ultraviolet and blue part of the spectrum. Even after the effects of distance and interstellar extinction are taken into account, it remains intrinsically tens of thousands of times more luminous than the Sun. The star's large radius means that its surface lies far from the centre compared with a main sequence star of similar mass. This expansion is a consequence of changes in the stellar interior as nuclear fusion proceeds. In the core, hydrogen fuses into helium through chains of reactions that are efficient at high temperature, and the energy released must be transported outward through the overlying layers. As the chemical composition of the core changes and the balance between pressure and gravity shifts, the outer envelope responds by puffing up. In a supergiant, this envelope is extended and relatively rarefied compared with the dense centre, so the surface gravity at the photosphere is lower than in a more compact star of the same mass. The combination of high luminosity and low surface gravity has important consequences for the behavior of the outer layers. The intense radiation field exerts pressure on the gas, especially on ions of heavier elements that have many absorption lines in the ultraviolet. When these ions absorb photons, they gain momentum and transfer it to the surrounding material, driving it outward. The result is a powerful stellar wind that carries mass away from the star at speeds of hundreds to over 1,000 kilometers per second. Although the details of the wind structure belong to a later step in the exploration, the basic fact that the star continuously loses mass through an outflow is already fixed by its classification and measured properties. Inside the star, the core is dense and hot enough that nuclear reaction rates are extremely sensitive to temperature. Small changes in core conditions can lead to significant changes in energy generation, so the star responds by adjusting its internal structure until a new equilibrium between pressure and gravity is reached. For a massive star, the core burns hydrogen more rapidly than in a star like the Sun, so the main hydrogen burning phase is shorter in absolute time. In many models for a star of this mass and type, the overall lifetime on the hydrogen burning sequence is only a few million years, after which the core contracts and heats, further allowing fusion of heavier elements in successive stages. Indications from spectroscopy in comparison with evolutionary tracks suggest that the blue supergiant in Cygnus X-1 is already in a relatively advanced stage of hydrogen burning, or has just begun to evolve away from the simplest main sequence structure, although its exact evolutionary status remains a topic of detailed modelling. The star's atmosphere shows the imprint of its temperature-gravity and chemical composition. Its spectrum displays broad absorption lines from hydrogen and helium, together with features from ionized metals that help constrain the physical conditions in the outer layers. The widths and shapes of these lines are influenced by thermal motions, turbulence, and rotation. Measurements of line broadening indicate that the star rotates with a significant angular speed, though slower than many younger main sequence O-type stars. Rotation affects the distribution of temperature and brightness over the surface, and may also influence the geometry of the wind. In addition, some line strengths and ratios point to processed material from the stellar interior being mixed into the envelope, which is expected for evolved massive stars where convection or rotational mixing brings fusion products closer to the surface. In its local neighbourhood, the blue supergiant sits among other massive stars that formed from the same general region of the Milky Way disk. Its motion through space reflects both the common motion of its parent association and the additional velocity gained from interactions within the binary and the wider environment. Proper motion and radial velocity measurements place it at a distance of several thousand light-years, and show that it orbits within the galactic potential in a way similar to other young massive stars in the same sector. This context helps astronomers calibrate models of its age and initial mass, because the properties of the surrounding stellar population provide independent clues to the time since the parent cloud fragmented and collapsed. The gravitational field of the supergiant defines a region around it within which gas and small bodies remain gravitationally bound if they move slowly enough relative to the star. For an isolated object, this region would host any planet's debris or circumstellar material that might have formed alongside the star. In a close binary, the situation is more complex because the gravitational influence of the companion must also be considered. The concept of gravitational domains is then described in terms of lobes of influence surrounding each star. Although this section does not yet track the details of the binary orbit, it is already clear that the size and mass of the blue supergiant give it a dominant role in shaping the local gravitational and radiative environment. Its luminosity heats nearby gas and dust. Its radiation pressure contributes to the dynamics of any surrounding material, and its evolving interior sets the pace at which its structure and output change over time. Even without reference to compact companions or accretion processes, the star itself is a complex laboratory of high-mass stellar evolution, with a stratified interior, a bright and extended atmosphere, and a continuous outflow that carries mass and energy into the surrounding space. Measurements across the electromagnetic spectrum from ultraviolet and visible light to infrared and radio build up a consistent picture of a luminous, hot and evolving supergiant whose physical properties match those expected for a massive star in this stage of life. The presence of a hidden compact companion in the Cygnus X-1 system is inferred from the motion of the blue supergiant rather than from any direct image of the second object. When astronomers record spectra of the star over many nights, and measure the positions of absorption lines with high precision, they find that these lines shift back and forth in wavelength with a regular period. This behavior indicates that the star moves toward and away from the solar system in a repeating pattern, which is naturally explained if it is orbiting around a common center of mass with an unseen partner. By tracking the speed of this radial motion and the length of the cycle, researchers determine the orbital period and a minimum estimate for the mass of the companion. In the case of Cygnus X-1, the period is only a few days, which implies a compact orbit with the two components separated by a distance comparable to a small fraction of the Earth-Sun separation. Combined with the mass and motion of the supergiant, the inferred mass of the unseen object is many times that of the Sun, comfortably above the maximum mass that stable neutron star models allow. This strongly points to a stellar mass black hole, an object whose gravity is so intense that no radiation escapes from within its event horizon, leaving only its gravitational influence and the behavior of nearby matter as observable signatures. The orbit of the system can be described by two bodies moving in ellipses around their mutual center of mass. For Cygnus X-1, the orbit is close to circular, so the separation between the star and the compact object changes only modestly over each cycle. The blue supergiant traces a small circle or ellipse whose size is set by the ratio of its mass to that of the companion, while the compact object traces a larger motion on the opposite side of the center of mass if it is less massive, or a smaller one if it is more massive. In this system, the compact object is less massive than the star, but still heavy, so both move perceptibly, and the observed motion of the star encodes the gravitational pull of the unseen companion. The orbital plane has some tilt with respect to the line of sight, so the full three-dimensional motion is not directly visible, but modelling can account for this inclination. Constraints from light curves, spectroscopy and other data together point to an inclination that is neither edge-on nor face-on, which avoids deep eclipses, but still allows measurable radial velocity shifts. The blue supergiant does not appear as a perfect sphere in this configuration. Because it orbits close to its companion, the gravitational field across its volume is not uniform. The side facing the compact object feels a slightly stronger pull than the far side, and the star deforms slightly, becoming elongated along the line connecting the two bodies. This tidal distortion leads to a shape that resembles an ellipsoid rather than a sphere. As the star rotates around the center of mass, different aspects of this elongated shape present different projected areas to the line of sight, causing small regular changes in the observed brightness, even if the intrinsic luminosity stays constant. These ellipsoidal variations provide additional information about the degree of distortion and indirectly about the closeness of the orbit and the masses involved. A useful way to describe the gravitational domains in such a system is through equipotential surfaces, which define regions inside which material remains bound to one star or the other. One special surface passes through saddle points between the two bodies and encloses separate lobes around each object. The volume inside each lobe is the region where matter at rest relative to the orbit would remain gravitationally attached to that component. For the blue supergiant in Cygnus X-1, its lobe is large but finite. Current measurements indicate that the star does not quite fill its entire lobe, so mass loss proceeds primarily through a stellar wind rather than through direct overflow at the inner saddle point. Even so, the proximity of the lobe boundary to the stellar surface means that gas leaving the star can more easily be influenced by the gravity of the compact object than it would in a wider binary. The orbital motion is rapid on human timescales, but slow compared with the dynamical timescale of the inner parts of the star. With a period of a few days, each complete circuit represents a small step in the stellar lifetime, which extends over millions of years. Over many orbits, the exchange of mass and angular momentum between the components can gradually alter the orbit, but at any given moment it remains close to a stable repeating configuration, described by a well-defined period and separation. Small deviations from a perfect Keplerian ellipse may arise from mass loss mass transfer or additional forces, yet the first-order picture of two bodies in mutual orbit captures most of the observed behavior. The compact object itself does not emit light that can be resolved as a stellar spectrum, so its presence is detected only through its gravity and through radiation from nearby matter, which other sections will examine in more detail. In this section, the focus remains on how the motion of the supergiant and the overall brightness variations together demonstrate the existence of a massive unseen companion and define the basic geometry and timescale of their orbit. The estimates for the masses and orbital parameters depend on several measured quantities, including the distance to the system, the inclination of the orbit, and the detailed properties of the supergiant itself. Each of these inputs carries some uncertainty, so different analyses can yield slightly different preferred values for the black hole mass and for the exact size of the orbit. Even with these uncertainties, all reasonable combinations of parameters place the mass of the compact object well above the regime where neutron stars remain stable in modern theoretical models. This robustness is one reason Cygnus X-1 is treated as a clear example of a stellar mass black hole in a high-mass X-ray binary, with the binary orbit providing the fundamental dynamical evidence for the nature of the hidden companion. The blue supergiant in Cygnus X-1 does not keep all of its outer layers bound tightly to its surface. The combination of high luminosity and relatively low surface gravity allows radiation from the star to push material outward and launch a continuous stellar wind. A stellar wind in this context is a flow of gas that escapes from the star in all directions, carrying mass away into the surrounding space. In the outer atmosphere, ions of heavier elements absorb ultraviolet photons in many spectral lines. Each absorption event transfers momentum from the radiation field to the ion, and repeated interactions accelerate the gas to high speeds. As the gas moves outward and density drops, the wind reaches a roughly steady outflow speed of hundreds to more than 1,000 kilometers per second, depending on direction and local conditions, so the material quickly leaves the immediate vicinity of the star. The mass loss rate, which is the amount of mass carried away per unit time, is large compared with that of the Sun, though still small compared with the total mass of the supergiant. Over the lifetime of the star, however, this process removes a significant fraction of its outer envelope. Closer to the surface, the wind starts as a subsonic, slowly accelerating flow. As it climbs out of the gravitational potential well, it passes through a critical point where the speed reaches the local sound speed, then becomes supersonic farther out. In this regime, the wind can sustain shocks and density variations that propagate outward. Line-driven winds of this kind are prone to instabilities, because small irregularities in density and velocity can grow as radiation interacts differently with slightly denser or thinner parcels. As a result, the wind is not perfectly smooth. Instead, it contains clumps and rarefied regions with local variations in density superposed on the average decline with distance from the star. These clumps can affect how the wind interacts with the compact object and how radiation from the inner binary escapes, but at the scale of the entire system, the wind still fills the space around the star with a roughly quasi-spherical outflow. In a binary like Cygnus X-1, the wind does not expand into an empty static environment. The compact object orbits nearby, and the whole system moves through the interstellar medium. The relative motion between the star and the surrounding gas can produce a bow shock, where the stellar wind meets interstellar material, shaping an outer boundary where the outflow slows and merges with the ambient medium. Inside that scale, the wind remains dominated by the star's radiation and gravity. In the frame that rotates with the binary, the outflowing gas feels not only the gravitational pull of the two bodies, but also apparent forces due to rotation. These additional influences slightly deflect the trajectories of wind parcels and can create spiral patterns or asymmetries in the density distribution, especially when the orbital period is short compared with the time it takes the gas to travel a few stellar radii. the compact object exerts its own gravitational force on the wind, bending the paths of parcels that pass near it. Even before any material becomes bound and forms an accretion flow, there is a region in which the wind density and velocity field are noticeably distorted. Gas that originates from the hemisphere of the star facing the compact object is more likely to be deflected inward than gas launched from the far side, so the density of wind material between the two bodies can become higher than in regions farther away. The orbital motion further modulates this distribution as the star and compact object change relative positions along their orbit, though in a nearly circular system the pattern reaches a repeating configuration over many cycles. The temperature of the wind near the star is relatively high, but as the gas expands it cools both through adiabatic expansion and through radiative processes. Embedded shocks from instabilities can locally reheat portions of the flow, creating small regions of higher temperature. The ionization state of the wind is set by the balance between heating from radiation and cooling through emission. Where the star's ultraviolet field dominates, the wind remains highly ionized, with hydrogen and helium mostly stripped of electrons. Closer to the compact object, X-rays from accreting material near the black hole add another source of ionizing radiation. This leads to an ionization structure that is not purely radial, but depends on the angle relative to both sources. For example, there can be a zone where X-ray illumination is strongest on the side of the wind that faces the compact object, while the star's own radiation maintains a different ionization state on the opposite side. This structure affects the wind opacity, the efficiency of radiative driving, and the cooling rates. Observations of absorption, lines in the spectrum of the system including lines that shift and change shape with orbital phase, provide evidence for such complex wind conditions. By modelling these features, astronomers infer wind velocities, densities, and ionization levels at different positions around the binary. They find that the wind is dense enough near the star to supply substantial mass, yet extended enough that material can travel many stellar radii before interacting strongly with the compact object or with the interstellar medium. The density falls with distance from the star, so regions close to the stellar surface contribute most of the mass that is available for any later capture. At larger distances, the wind blends smoothly into the general environment. X-ray observations from the vicinity of the compact object must pass through varying columns of wind material as the system orbits. This leads to changes in the amount of absorption seen at different orbital phases. When the compact object lies behind the star from the perspective of the observer, the line of sight passes through denser parts of the wind and perhaps through regions shadowed from some radiation, producing stronger absorption and scattering. When the compact object moves to the near side, the path crosses less dense material, and the observed spectrum shows less attenuation. These effects allow the spatial distribution of wind density to be probed indirectly, adding to the information obtained from optical and ultraviolet spectroscopy of the star itself. The net result is a shared environment, in which the blue supergiant continuously injects mass momentum and energy into the space around both components of the binary, through its wind establishing the conditions under which more focused flows and accretion structures can later develop closer to the compact object. Close to the compact object, the roughly spherical outflow from the blue supergiant is reshaped by gravity into a more directed flow. Gas parcels in the stellar wind leave the surface with a range of initial directions and velocities, but those that pass within a certain distance of the black hole feel a significant deflection toward it. This distance is often described in terms of a capture radius set by the mass of the compact object and the relative speed of the wind. Within this scale, the gravitational pull is strong enough that the trajectories of many parcels bend away from simple radial expansion and begin to curve inward. The flow pattern in this regime differs from the more symmetric configuration around an isolated star. Instead of a nearly uniform density at a given distance, there is a preferred direction in which gas densities become higher, roughly along the line connecting the supergiant and the compact object. Gas that starts from the hemisphere facing the black hole has a greater chance of entering this region than gas from the far side, and as a result, the space between the two bodies hosts a focused stream in which wind material is funneled toward the gravitational well. The motion of the gas in this focused flow can be treated to first approximation as that of test particles moving in the combined gravitational field of the two bodies, while also experiencing the effect of orbital motion. In the frame that co-rotates with the binary, the flow pattern can appear nearly steady with streamlines that curve smoothly from the vicinity of the star toward the compact object, and then continue onward. Some parcels pass near enough to become gravitationally bound, while others remain unbound and continue outward after being deflected. Hydrodynamic simulations of similar systems show that the interaction region between the wind and the compact object often contains a bow-shaped shock front. As the wind collides with material that is already falling inward, or with gas that has been slowed by gravity, shock waves form and convert kinetic energy into thermal energy. This heating raises the temperature of the gas in the immediate interaction zone, making it more ionized and altering its emission properties. The shock structure is not static in detail. It can oscillate or shift position slightly as conditions in the wind and accretion flow vary, but on timescales shorter than the orbital period, the overall pattern remains recognizable as a region of enhanced density and temperature around the accretion focus. The focused stream itself is not a narrow, rigid structure. It has a finite width, set by the range of initial directions and velocities of the contributing wind parcels, and it broadens as it travels. Within this stream, density is higher than in surrounding portions of the wind at the same distance from the star, and velocity vectors are biased toward the compact object. Turbulent motions arise where gas with slightly different speeds and directions interacts, and small-scale instabilities grow where shocks and shear layers are present. These processes break the flow into clumps and filaments, while still preserving the overall sense of a directed inward movement. Observationally, the presence of a focused wind is inferred from how absorption features and X-ray spectra change with orbital phase. When the line of sight from the compact object to the observer passes through the denser part of the stream, X-rays from near the black hole must traverse more material, leading to stronger absorption at low energies. At other phases, the line of sight intersects less of the focused gas, and the level of absorption decreases. By tracking these changes over many orbits, astronomers construct models of the density distribution around the compact object and test whether a focus stream configuration matches the data better than a strictly symmetric wind. The models that best fit the observations indicate that the outflow from the star is not uniform, but is shaped into a denser region that roughly follows the path connecting the two components. The interaction between the focused stream and the orbital motion adds further structure. As the compact object moves along its nearly circular path, the stream does not point to a fixed location in space, but continually adjusts to the changing position. In the co-rotating frame, this produces a curved flow that can wrap partly around the compact object and in some cases trail behind it in a wake. Gas in this wake may have been partially focused and then stripped away or left behind, forming regions of elevated density downstream. These features can affect how radiation from the vicinity of the black hole escapes, and may contribute to variability in observed flux when parts of the wake cross the line of sight. The detailed balance between focused inflow and outflowing wind depends on the mass loss rate of the star, the speed of the wind, and the orbital parameters. If the wind is faster, gas parcels spend less time in the region, where gravity can deflect them and the effective capture fraction is smaller. If the wind is slower, gravity has more opportunity to bend trajectories inward, and a larger portion of the outflow can join the focus stream. For Cygnus X-1 measured wind speeds and mass loss rates indicate that a non-trivial fraction of the wind is available to be captured within the gravitational radius of the compact object, even though the majority of the outflow ultimately escapes to large distances. The focus stream is therefore an efficient channel that supplies gas to the capture region, without requiring the star to overflow its gravitational lobe. The thermodynamic state of the gas in the stream evolves as it approaches the compact object. At first, conditions resemble those in the general wind with high ionization, driven by the star's radiation and moderate temperatures. As the gas moves inward and passes through shocks, its temperature can rise, and the radiation environment changes as X-rays from near the black hole become more intense relative to the stellar ultraviolet. Ionization stages shift, and certain species become more or less abundant in particular charge states. These changes leave signatures in absorption and emission lines that can be studied spectroscopically. For example, variations in the strengths and profiles of lines from highly ionized elements as a function of orbital phase reveal where along the flow these ions are most prevalent. Combining such measurements with models of the flow geometry allows a three-dimensional picture of the focus stream to be assembled at least in broad outline. On smaller scales, the interplay between radiation forces, gravity and gas pressure introduces further complexity. The X-ray flux from the vicinity of the compact object can reduce the effectiveness of radiative driving in parts of the wind by ionizing atoms that would otherwise contribute to line absorption. This can locally alter the acceleration of the wind and modify the density profile along the stream. Some regions may experience partial stagnation or slower acceleration, while others continue to flow more freely. These feedback effects couple the properties of the accretion-powered emission near the compact object to the structure of the inflowing gas that supplies it. Despite this complexity, the essential role of the focus stream remains clear. It concentrates a portion of the wind into a denser inward-directed flow that delivers material into the gravitational sphere of influence of the compact object and sets the conditions for the formation of the bound accretion structures examined in the next layer inward. Around the compact object in Cygnus X-1, there is a region where the character of the gas flow changes from an almost free wind into material that is gravitationally bound. Far from the black hole, wind parcels move on nearly straight paths, altered only slightly by the combined gravitational pull of the two bodies. As they approach the compact object, its gravity becomes the dominant influence, and trajectories begin to curve more strongly. A useful way to think about this transition is to consider an effective capture radius within which the gravitational potential of the black hole is strong enough to draw in gas despite its initial outward speed. This radius depends on the mass of the compact object and on the relative velocity of the wind and orbital motion, and for a black hole of roughly 21 solar masses in a fast wind, it extends over a region comparable to a few times the characteristic scale of the binary separation. Gas that passes inside this radius with a moderate impact parameter can be deflected into bound orbits, while gas that remains outside continues on unbound paths, eventually merging back into the more general wind. The motion of gas inside the capture region is not a simple radial infall. The wind that approaches the compact object carries net angular momentum, because the star, the black hole, and the wind itself are all in motion relative to one another. Parcels of gas that originate on different parts of the stellar surface reach the vicinity of the black hole with slightly different directions and speeds. Even if the wind appears nearly symmetric at larger scales, these small differences mean that once gravitational focusing acts, the captured material does not fall directly inward along straight lines, but instead follows curved trajectories. In many cases, the orbits are initially highly elongated, with gas moving on plunging paths that swing close to the compact object at pericenter, and then, if not further dissipated, would carry it back outward. However, the gas is not collisionless. As different streams of material converge, they intersect and interact, producing shocks where velocities change abruptly and kinetic energy is converted into heat. Within the capture region, there is thus a complex pattern of inflow, with streams that cross shocks that form and dissipate, and a gradual redistribution of energy and angular momentum as gas parcels exchange momentum with one another. Hydrodynamic simulations of wind accretion onto a compact object illustrate that a bow shock frequently forms upstream of the accretor, where the incoming flow first encounters material already influenced by gravity. Behind this shock in the wake of the compact object as it moves through, the wind gas slows, compresses and reaches higher temperatures. The density in this wake is higher than in the surrounding wind, and the flow becomes more irregular. Some of the material in this shock-heated region is deflected around the black hole and escapes downstream, while some loses enough energy to become gravitationally bound and spiral inward. The structure that results is three-dimensional and time-dependent, with eddies and vortices that evolve continuously as the conditions of the incoming wind fluctuate. The temperature of the gas in the immediate post-shock region rises significantly compared with the unshocked wind. Compression and heating lead to higher ionization states, and the gas can emit radiation in X-ray and ultraviolet bands. However, in the outer parts of the capture region, much of this emission is still relatively faint compared with the intense radiation that originates closer to the compact object, where densities and temperatures become still higher. In this layer, the conversion of kinetic energy into thermal energy is ongoing but incomplete, so the gas is in a state of partial settling. Its pressure and temperature profiles adjust under the combined influence of gravity and radiative cooling. Over time, energy is radiated away, and gas moves inward along paths that gradually circularize. The angular momentum distribution of the captured material is crucial in determining how the flow evolves. If the net angular momentum were extremely small, the gas could fall nearly radially inward and be accreted with only modest organization into a rotating structure. In a system like Cygnus X-1, the orbital motion of the compact object through the wind ensures that the captured gas has a measurable net angular momentum, although individual parcels may deviate from the mean. As collisions and shocks redistribute momentum, some gas loses angular momentum and moves closer to the compact object, while other gas gains angular momentum and can be flung outward or maintain a larger orbit. The overall effect is a gradual segregation, with inner regions becoming more rotationally supported, while outer regions retain a more chaotic mix of inflow and outflow. The timescales that govern this settling process differ from the orbital period of the binary. The free-fall time from the capture radius to the innermost orbits is typically much shorter than the time required for the star and compact object to complete a full circuit around their common center of mass. This means that the inner part of the capture region can respond relatively quickly to changes in the incoming flow. At the same time, variations in the stellar wind or in the focusing geometry caused by slow changes in the orbit can modulate the supply of gas on longer timescales. As the system evolves, the average capture rate can remain roughly steady, while fluctuations on shorter intervals produce changes in density and temperature that lead to corresponding variations in observed emission. The geometry of the captured flow is influenced not only by gravity and hydrodynamics, but also by the radiation field emerging from closer to the black hole. X-rays emitted from the inner accretion region travel outward and interact with the inflowing gas. This radiation can heat and ionize the material, modifying the cooling rates and changing the way line driving and other radiative processes operate. In some parts of the capture region, high ionization reduces the number of bound electrons available for line absorption, which can weaken the radiative acceleration that helped to launch the wind in the first place. This back reaction can lower the effective wind speed locally and make it easier for gravity to capture more material. In other zones, heating can increase pressure and help drive gas away. The result is a feedback loop in which the brightness and spectrum of the inner flow influence the structure of the outer inflow that feeds it. Observational signatures of the capture region appear in the way X-ray spectra, and light curves change with orbital phase and over longer intervals. Absorption by partially ionized gas in the capture zone imprints features on the X-ray spectrum that differ from those produced by the more distant stellar wind alone. Some lines and edges arise from ions with charge states that are characteristic of intermediate temperatures and densities, suggesting that the gas has been processed by shocks and X-ray illumination, but has not yet reached the extreme conditions near the compact object. Time-resolved spectroscopy reveals that these features can strengthen, weaken or shift as the binary rotates and as the density and ionization state of the capture flow change. By comparing such observations with models that track gas along ballistic and hydrodynamic trajectories in the gravitational field of the compact object, researchers estimate the size, shape and physical conditions of the capture region in Cygnus X-1. Within the bounds of this region, the crucial transition occurs from a stellar wind that mainly escapes to infinity to a population of gas that is bound and destined to move inward on progressively tighter orbits under the influence of gravity collisions and radiation, forming the basis for the more organized accretion structures that exist closer to the black hole. Within the region where gas becomes gravitationally bound to the compact object, the flow gradually changes from a chaotic wake into a more organized rotating structure. After passing through shocks and intersecting streams in the capture zone, many parcels of wind material retain enough angular momentum that they cannot fall directly inward. Instead, their orbits curve around the black hole with pericenters that lie at distances, where the gravitational field is strong but not yet extreme. Collisions between parcels on different trajectories together with shock dissipation reduce the random components of their motion, while leaving the net rotational component largely intact. Over many orbital times at these radii, this process encourages the gas to settle toward a preferred plane perpendicular to the average angular momentum vector of the captured flow. The result is the gradual formation of an outer accretion structure with a flattened disk-like geometry, though it may still be geometrically thick and noticeably asymmetric. The gas in this region does not instantly arrange itself into a smooth, steady disk. Because the inflow is supplied by a stellar wind rather than by matter that streams through a narrow point from the star's surface, the feeding is inherently three-dimensional and somewhat irregular. Fresh material arrives with a range of angular, momentar and impact parameters, so the outer structure carries imprints of this variability. In hydrodynamic models of wind-fed accretion, the outer flow often appears as a lopsided, clumpy configuration in which denser arcs and filaments orbit the compact object, while lower density regions occupy the spaces between. These features can persist for several orbital periods, slowly evolving as ongoing collisions and radiative cooling smooth some inhomogeneities and create others. Despite the irregularities, an overall pattern emerges in which most of the bound gas participates in rotation around the compact object, and the typical orbital speed increases as distance decreases. At any given radius in the outer structure, gas follows approximately circular or slightly elliptical paths under the influence of gravity and pressure. The orbital period at these distances is short compared with the binary period, but long compared with the dynamical timescale near the innermost orbits. As gas moves on these paths, it experiences shear because the orbital speed changes with radius. Inner rings move faster than outer rings. This differential rotation stretches any initially compact density feature into an elongated spiral pattern. Where neighbouring streamlines slide past each other with different speeds, velocity gradients arise. If the fluid were perfectly smooth and free of internal stresses, matter would remain on its original orbit indefinitely. In a real plasma microscopic viscosity turbulence, and magnetic stresses all contribute to the transport of angular momentum. The detailed mechanisms of this transport are complex and involve processes such as magnetorotational instability in magnetized disks, but in a descriptive sense the effect is that some gas loses angular momentum and drifts inward, while other gas gains angular momentum and moves outward. In the outer accretion structure, this redistribution proceeds slowly compared with the orbital motion, so the disk-like flow can be described as quasi-steady over a number of orbits. The temperature of the gas at these radii reflects a balance between heating and cooling. Heating arises from the conversion of orbital energy into thermal energy through shocks, turbulent dissipation, and viscous processes. As gas spirals inward, a fraction of the gravitational potential energy released along the way is converted to heat in the disk. Cooling occurs as the gas radiates this energy away mainly in ultraviolet optical and soft X-ray bands depending on local density and ionization state. In the outer parts of the structure where orbital speeds are lower and the gravitational potential is shallower, the energy release per unit mass is modest compared with that in the innermost regions. Consequently, temperatures there are high compared with the original stellar wind but lower than those near the black hole. The disk surface can host layers where line emission from various ions is strong, while deeper layers may be more nearly in thermal equilibrium at temperatures set by the balance between internal heating and radiative losses. The vertical thickness of the outer accretion flow depends on the ratio of gas pressure to gravity. At relatively low temperatures and high densities, gas settles closer to the midplane, producing a thinner, more flattened disk. If heating is strong or radiation pressure becomes significant, the structure can puff up into a thicker configuration. In wind-fed systems where the supply of material is variable and the ionizing radiation field is strong, the outer flow often takes the form of a moderately thick disk or torus with an extended atmosphere. This atmosphere can be photoionized by X-rays from closer to the black hole, creating a layered structure in which cooler, denser material near the midplane is overlain by hotter, more tenuous gas. The interface between these layers can be unstable, giving rise to waves, corrugations, and small-scale turbulence. Observational evidence for an outer accretion structure comes from optical and ultraviolet spectra that show emission lines broadened and sometimes double-peaked, which is characteristic of rotating gas. In such a configuration, material on one side of the disk moves slightly toward the observer, while material on the opposite side moves slightly away, so the line profile gains contributions from a range of Doppler-shifted velocities. The resulting shape can reveal the characteristic orbital speeds at the radii where the line is formed. In Cygnus X-1, several lines associated with hydrogen and helium show profiles consistent with emission from a rotating extended flow rather than solely from the stellar atmosphere. By modelling these lines, astronomers estimate the size scale and kinematics of the outer disk. They find that the disk is relatively compact compared with those in systems where mass transfer occurs directly through a narrow stream from the star yet still large enough to host a radially extended region of rotating gas. Time variability provides further clues. Changes in the equivalent widths and shapes of emission lines over days to weeks suggest that the outer accretion flow is not static. Variations in the supply of gas from the wind modulations in the ionizing X-ray flux and the growth and decay of local density enhancements all contribute to a pattern of fluctuations in the observable properties. Some of these changes may correspond to waves or spiral structures propagating through the outer disk, excited by the gravitational influence of the companion star or by internal instabilities. Others may reflect the passage of clumps from the capture region into the disk, temporarily altering local densities until they are sheared apart by differential rotation. The overall mass contained in the outer accretion structure is small compared with the mass of either the black hole or the blue supergiant, but it is significant relative to the amount of matter accreted over characteristic timescales for luminosity changes. This means the disk can act as a reservoir that buffers short-term fluctuations in the incoming wind, smoothing some variations, while still transmitting longer timescale changes inward. The radial distribution of surface density, temperature, and angular momentum in this region sets the boundary conditions for the hotter inner disk. At the same time, radiation and outflows from smaller radii can travel outward and influence the outer flow by altering its ionization state and heating pattern. The outer accretion structure around the compact object is therefore a dynamic rotating region, where captured wind material first settles into a coherent disk-like configuration, its properties shaped by the balance between gravity rotation, internal stresses and radiative processes as it continues to move towards smaller orbits, under the pull of the central mass. Closer to the compact object in Cygnus X-1, the rotating gas settles into a more clearly defined inner accretion disk, where orbital motion dominates over random motions, and the release of gravitational energy becomes much more efficient. In this region, matter orbits the black hole on nearly circular paths with orbital speeds that rise as the radius decreases. For a black hole of roughly 21 solar masses, these speeds reach a significant fraction of the speed of light at radii only a few times larger than the innermost stable orbit, allowed by general relativity. The gas in the inner disk is therefore moving rapidly through a strong gravitational field, and the changing balance between orbital energy, internal pressure, and radiation shapes both its structure and its emission. At each radius, gravity supplies a reservoir of potential energy that can be tapped as gas slowly spirals inward under the influence of viscous and magnetic stresses. A portion of this energy is converted into heat within the disk, raising the temperature of the gas, while another portion is transported outward with angular momentum. Because the gravitational well deepens steeply toward the black hole, the energy released per unit mass rises sharply as gas approaches the inner edge of the disk. This leads to a radial temperature gradient in which outer regions are relatively cooler, and inner regions become very hot, with characteristic temperatures in the inner disk high enough that the peak of the emitted spectrum lies in X-ray energies, rather than in ultraviolet or visible light. The disk in this zone is dense and optically thick, meaning that photons produced in the midplane are absorbed and re-emitted many times before escaping from the surface layers. Under such conditions, the vertical structure of the disk is set by a balance between gravity pulling material toward the midplane and pressure pushing outward. Gas pressure, and in parts of the flow radiation pressure together, support the disk against its own weight. The scale height, which measures the thickness of the disk, remains small compared with the radius in classical thin disk models, so the geometry is often approximated as a flattened structure with a shallow vertical extent. In practice, the thickness can increase where radiation pressure becomes important, or where additional heating raises the sound speed, so the inner disk in a system like Cygnus X-1 may be moderately thicker than the outer parts, while still retaining a clear midplane and a predominantly rotational support. The temperature at different depths within the disk also varies. Near the midplane densities are highest, and the gas can be partially shielded from direct irradiation by the innermost regions, while closer to the surface, where the optical depth drops, photons escape more readily, and the local temperature reflects both internal heating and external illumination. The emergent radiation from the disk's surface can be approximated as a sum of contributions from a series of concentric annuli, each with its own effective temperature set by the local balance between heating and cooling. In the inner disk, these effective temperatures reach values where thermal emission extends into the soft X-ray range, producing a smooth continuum that rises and falls in energy according to the temperature profile. Observationally, this component appears as a disk-like spectrum whose shape can be fitted with models of an optically thick, geometrically thin accretion disk. By adjusting parameters such as the inner radius, the temperature at that radius and the inclination of the disk, astronomers infer properties of the inner flow and place constraints on the black hole mass and spin. For Cygnus X-1 fits to such models in certain spectral states suggest an inner disk that extends close to the innermost stable orbit, and temperatures of several million degrees in the hottest zones, although precise values depend on assumptions about distance inclination and the contribution of other emission components. The high orbital speeds in the inner disk introduce relativistic effects even before the flow reaches the region, where gravity is strong enough to warp space-time dramatically. Doppler shifts broaden the emission lines produced in the disk surface because material on the side approaching the observer has its radiation shifted to higher energies, while material on the receding side has its radiation shifted to lower energies. In addition, light emitted from deep in the gravitational potential well experiences gravitational redshift, which moves photons to lower observed energies compared with their energy at the point of emission. When these effects are combined over all parts of the disk, the resulting line profiles become skewed and extended, with a characteristic blend of blue shifted and red shifted wings. In some X-ray spectra of Cygnus X-1, broadened iron lines provide evidence of such relativistic shaping, indicating that the inner disk reaches close to the black hole, where both orbital speeds and gravitational redshift are significant. The inner disk is not perfectly steady. Small fluctuations in the rate at which gas is supplied from larger radii, local instabilities in the balance between heating and cooling, and variations in magnetic stresses all cause the surface density and temperature to vary as a function of time and radius. Because the orbital timescales in the inner regions are short, these disturbances can grow and propagate rapidly. Changes in density or temperature at a given radius alter the local emissivity, while changes in the accretion rate modify the amount of gravitational energy released per unit time. The result is variability in the emitted X-ray flux on timescales, ranging from fractions of a second to many hours. Some of this variability appears as broad band noise, reflecting the superposition of many small stochastic fluctuations, while other components appear as quasi-periodic oscillations, where the luminosity shows preferred timescales associated with characteristic frequencies in the disk. In Cygnus X-1, rapid variability is a persistent feature of the X-ray light curve, indicating that the inner accretion flow is dynamic rather than static. The physical state of the inner disk can change over longer intervals as well, leading to distinct spectral states, in which the relative contributions of different emission components vary. In configurations where the optically thick disk extends inward nearly to the innermost stable orbit and radiates efficiently, the spectrum tends to show a stronger thermal component associated with the disk, and the source may appear in a softer state. In other configurations, the inner disk becomes cooler or less extended, and a harder component associated with hotter, lower density regions of the inner flow can dominate the high energy emission. Transitions between these states involve changes in the distribution of temperature, density, and geometry in the inner accretion flow. Although the detailed mechanisms that trigger and regulate such transitions remain an active area of research, the general picture is that moderate changes in mass accretion rate and in the balance between heating and cooling can rearrange how energy is partitioned within the inner disk and its immediate surroundings. From an energy budget perspective, the efficiency of accretion onto a black hole in this regime is significantly higher than that of nuclear fusion in stars, meaning that a relatively small mass inflow through the inner disk can power the observed luminosity of Cygnus X-1. The detailed structure of this region, including its temperature profile, thickness, and inner radius, determines how efficiently the inflowing gas converts gravitational energy into radiation and sets the characteristic brightness and spectral shape of the emission emerging from the immediate environment of the black hole. Above and below the inner accretion disk in Cygnus X-1, there is a region of hot dilute gas often described as a corona. In this zone, the density of matter is lower than in the disk midplane, but the typical particle energies are much higher, so that electrons and ions move at high speeds and the temperature reaches tens to hundreds of millions of degrees. The gas is optically thin in many directions, meaning that photons can cross significant distances without being absorbed, and this allows the corona to act as an intermediate layer where radiation from the disk and radiation generated inside the hot plasma interact. The exact geometry of the corona is not directly imaged, but theoretical models and spectral fits suggest that it can take the form of a vertically extended region, above the inner disk a collection of compact active zones, or a combination of both. In all these pictures, the corona sits close enough to the inner accretion flow that it is immersed in intense soft photons from the disk surface and in strong gravity from the black hole. The energy that maintains the corona in such a hot state comes from the accretion process itself. As gas in the disk moves inward, magnetic fields embedded in the plasma can be twisted and stretched by differential rotation. This can generate magnetic stresses that transport angular momentum and also release energy when field lines reconnect. Part of this released energy heats the upper layers of the disk atmosphere and lifts material into a hot tenuous phase forming the corona. In addition, turbulence in the inner flow can drive vertical motions that carry energy out of the midplane. The balance between heating and cooling in this region sets the electron temperature, the density, and the overall size of the hot zone. Because the gas is optically thin, electrons can efficiently transfer energy to photons through a process known as inverse Compton scattering. Soft photons that originate in the cooler, optically thick disk enter the corona and encounter high-energy electrons. Each scattering event can boost the photon energy, and after multiple scatterings, some photons emerge as hard X-rays and even higher energy radiation. The resulting spectrum is broader and harder than the thermal emission from the disk alone, forming a power law-like component that extends to high energies with a cutoff set by the electron temperature and the optical depth of the corona. Observations of Cygnus X-1 in certain spectral states show just such a component with a strong high-energy tail that is well explained by Comptonization in a hot optically thin plasma near the black hole. Not all photons escape directly after passing through the corona. A fraction of the hard X-rays produced in the hot gas travel back toward the disk and are absorbed or scattered in the cooler, denser material. This interaction heats the disk's surface layers and produces a reflected spectrum that contains both a continuum and discrete features, including fluorescence lines from iron and other elements. Because the disk is rotating rapidly and lies in a region of strong gravity, these lines appear broadened and skewed. The reflected component therefore carries information about the geometry of the corona, the inclination of the disk, and the location of the reflecting material. In Cygnus X-1 fits to spectra that include both a Comptonized continuum and a reflection component suggest that the corona covers at least part of the inner disk, and that its characteristic size is only a few tens of gravitational radii. Within the corona, the plasma conditions are not uniform. Numerical models indicate that the hot gas is likely to be structured into patches where magnetic reconnection and turbulent dissipation are especially strong. These active regions can flare when local magnetic fields rearrange, abruptly releasing stored energy and heating the electrons even further. Such events change the local emissivity and can contribute to short-term variability in the X-ray light curve. Because the electron cooling time through Compton scattering is relatively short in such an intense radiation field, the corona can respond on rapid timescales to changes in the disk emission and in the heating rate. This helps explain why Cygnus X-1 and similar systems show correlated variability between softer and harder X-ray bands with hard photons often lagging soft photons by small but measurable intervals that reflect the time spent by disk photons in the hot plasma. The corona is also closely linked to any outflows or jets that emerge from the inner accretion flow. In many accreting black hole systems, radio observations detect compact collimated outflows that appear to originate near the innermost radii. These jets carry matter and energy away from the system at high speeds and can emit synchrotron radiation from relativistic electrons spiraling in magnetic fields. In Cygnus X-1, persistent radio emission and resolved structures at larger scales indicate the presence of a relatively steady compact jet. The base of this jet is thought to lie near the corona, where magnetic fields anchored in the disk and threading the inner flow can channel some of the accreting material into an outflow. The same magnetic processes that heat the corona may therefore also help to launch the jet, though the detailed coupling between these components remains a subject of active research. Changes in the accretion rate and in the distribution of energy between the disk, the corona and the jet give rise to different spectral states of the system. In a so-called hard state, the corona is prominent, the inner disk may be truncated or cooler, and the high energy, Comptonized emission dominates the X-ray output, while compact radio jets are often strong. In a softer state, the optically thick disk contributes more of the X-ray luminosity, the corona becomes weaker or cooler, and the jet can be reduced or absent. Cygnus X-1 spends much of its time in a relatively hard state, with a bright corona and a stable jet, but it has also been observed to transition towards softer configurations, in which the thermal disk component is more pronounced. These changes likely reflect shifts in how accretion power is divided among the different channels, rather than abrupt alterations in the overall mass inflow. On short timescales, the corona behaves as a noisy dynamic medium. Fluctuations in density, temperature, and magnetic field strength modulate the production of hard X-rays, imprinting a complex pattern of variability on the light curve. Power spectra of the X-ray emission from Cygnus X-1 show broad noise components and at times weaker quasi-periodic features that may correspond to characteristic timescales in the inner flow and corona. Despite this complexity, the average properties of the corona over longer intervals can be described by relatively simple parameters, such as an effective electron temperature and optical depth, which are tuned in spectral models to reproduce the observed high-energy emission. In the immediate surroundings of the inner disk, this hot diffuse plasma supplies the hard X-ray component of Cygnus X-1 and provides the interface between the dense rotating flow and any outflows that draw on magnetic energy near the black hole. In the inner regions of the accretion flow around the black hole in Cygnus X-1, gravity is strong enough that the motion of matter and light must be described by general relativity rather than by simple Newtonian orbits. In this regime, the space-time around the compact object is curved by its mass, and spin and free-falling particles follow paths called geodesics that differ from the conic sections familiar from planetary motion. For a black hole with a given mass, there is a particular set of circular orbits that are stable, and another set that are unstable. At large, radii circular orbits are stable in much the same way as planetary orbits around a star, so a small inward or outward disturbance leads only to a gentle oscillation around the original path. Closer to the black hole, the curvature of space-time grows stronger, and the balance between centrifugal effects and gravitational attraction changes. There is a minimum radius at which a circular orbit remains stable for a given sense of rotation. Inside this innermost stable circular orbit, any small perturbation causes the orbiting matter to spiral inward, rather than settle into a new nearby circle. The position of this radius depends on the spin of the black hole, and on whether the orbiting matter moves in the same direction as the spin, or in the opposite direction. In a non-spinning case, the innermost stable orbit lies at a distance that can be expressed as a few times a characteristic gravitational radius related to the mass. If the black hole spins rapidly and the disk rotates in the same sense, the innermost stable orbit shifts inward, allowing matter to orbit closer to the event horizon before plunging. Observational studies of Cygnus X-1 that compare the X-ray spectrum and reflection features with theoretical disk models suggest that its black hole rotates rapidly, so the inner edge of the stable disk extends to radii only modestly larger than the horizon radius itself. Within the disk, gas at each radius moves on nearly circular paths, but the orbital speed and the gravitational redshift both increase as the radius decreases, so the physical conditions change steeply across the inner few radii near the innermost stable orbit. In these regions, the orbital period is very short, on the order of milliseconds to fractions of a second, which means that matter completes many revolutions while it spirals inward by a relatively small radial distance. The dissipation of energy through internal stresses continues to transport angular momentum outward, but as the flow approaches the innermost stable orbit, the nature of this transport changes. Outside that radius, the disk can maintain a nearly steady balance between inward mass flow and outward angular momentum flow, with viscous and magnetic stresses communicating forces between neighbouring rings. At the innermost stable radius, the supply of stable circular trajectories ends. Inside that point, material can no longer remain on a sustained nearly circular orbit, so once gas crosses this radius, it transitions into an inward plunge in which radial motion grows rapidly, and the time available for further dissipation becomes short. In many models, the torque exerted on the disk drops deeply inside the innermost stable orbit, because matter in the plunging region no longer shares its angular momentum efficiently with material farther out. In practice, magnetic fields and additional stresses may blur this transition to some extent, but the concept of a special radius marking the inner boundary of the efficiently radiating disk remains useful for interpreting observations. The amount of gravitational energy that can be converted into radiation before matter crosses this boundary sets an important efficiency scale for the accretion flow. Because the innermost stable orbit for a rapidly spinning black hole lies closer to the horizon than for a non-spinning one, the binding energy per unit mass at that radius is larger. This means that for the same mass accretion rate, a disk that extends down to a small innermost stable radius can radiate more energy than one that truncates farther out. Fits to the thermal and reflection components in the spectrum of Cygnus X-1 indicate that the inner disk often reaches very small radii, consistent with a high radiative efficiency, which supports the view that the black hole spin parameter is large. These inferences depend on detailed modelling and carry uncertainties, but they illustrate how the location of the innermost stable orbit links the strong gravity region to observable properties of the emission. The motion of small perturbations around circular orbits also changes character in this regime. In Newtonian gravity, radial and vertical oscillation frequencies around a circular orbit match the orbital frequency in a simple potential. In the curved space-time near a black hole, these frequencies differ and depend on radius and spin. This introduces natural timescales for various oscillatory motions within the disk, such as small radial epicycles or vertical warps. Some models for quasi-periodic features seen in X-ray variability of black hole binaries relate these oscillations to combinations of orbital radial and vertical frequencies at specific radii near the innermost stable orbit. In Cygnus X-1, the rapid structured variability suggests that the accretion flow responds sensitively to small changes in conditions in this strong gravity regime, although a single universally accepted explanation for all variability components does not yet exist. The gravitational potential in the inner region also affects the trajectories of photons emitted from the disk surface. While the detailed bending of light and the resulting appearance of the disk are examined in the next section, it is worth noting that the same curved spacetime that defines the innermost stable orbit also determines how light rays propagate. photons emitted from the receding side of the inner disk can be strongly redshifted and bent, while those from the approaching side are boosted to higher observed energies and can be focused toward particular viewing angles. The combination of these effects leads to characteristic broadening and skewing of emission lines that arise near the innermost stable orbit, and these line profiles in turn reveal the influence of strong gravity. In Cygnus X-1, the broad iron line observed in some spectral states is consistent with emission from radii comparable to a few times the event horizon radius, confirming that matter orbits in the part of spacetime where relativistic corrections are essential. The transition from the disk-like flow outside the innermost stable orbit to the plunging region inside it is not directly visible, but has consequences for timing and spectral behavior. As gas crosses the innermost stable radius and accelerates inward, the time between its last significant interactions with neighboring material and its arrival near the horizon is short. This can reduce the ability of the flow to smooth out small-scale fluctuations, allowing rapid changes in accretion rate at that radius to imprint themselves on the emitted radiation more directly. In addition, any inhomogeneities in density or temperature at the inner edge of the disk can move inward quickly, modulating the radiation produced in the corona and reflection components. The inner boundary of stable orbits therefore acts as a kind of dynamic transition layer, where the physical character of the flow changes from a comparatively steady, slowly evolving disk to a rapidly plunging infall. In the context of Cygnus X-1, this layer occupies a narrow radial zone, but plays a central role in setting how efficiently matter can radiate its orbital energy and how sensitively the emission responds to changes in the inflow. Near the black hole in Cygnus X-1, light does not travel along straight lines in the way it does far from strong gravitational fields. Instead, the curvature of space-time caused by the mass and spin of the black hole bends the paths of photons, changing both the direction in which they move and the energy they carry when they finally reach distant observers. General relativity describes this behavior by treating gravity not as a force acting at a distance, but as a geometric property of space-time where mass and energy determine the curvature and free particles follow the straightest possible paths in this curved geometry. For photons, these paths are null geodesics, and near a black hole they can differ markedly from the simple rays that would be drawn in flat space. In the region around the inner accretion disk, many photons originate from gas that orbits at radii only a few times larger than the event horizon. Some of these photons are emitted outward away from the black hole, while others are emitted in directions that initially point inward or sideways. Because the space-time curvature is strong, even photons that begin with trajectories directed outward can be bent back toward the black hole if they pass too close, while photons that begin with lateral directions can loop partially around the compact object before escaping. There exists a special set of photon trajectories associated with a photon orbit at a characteristic radius where light can in principle circle the black hole on unstable closed paths. In practice, small perturbations ensure that photons either spiral inward across the event horizon or move outward to infinity, but the presence of this photon orbit region has a strong influence on how the surroundings appear when viewed from a distance. The bending of light near the black hole means that the apparent shape and brightness distribution of the inner disk and corona differ from what would be expected if gravity did not curve space-time. Regions of the disk that would normally be hidden behind the black hole can become partially visible, because light from their surfaces is bent around the compact object and redirected toward the observer. As a result, more than half of the disk surface can contribute to the observed image, even for viewing angles that would show only one face of a flat disk in a Newtonian picture. In addition, rays from the far side of the disk can take multiple paths to reach the same observer, creating higher-order images in which the same physical region appears more than once at different apparent positions and with different magnifications. These higher-order contributions are typically much fainter than the primary image, because the path lengths are longer and the probability of escape without absorption is smaller, but they still play a role in shaping the detailed brightness profile near the apparent edge of the black hole. Gravitational redshift is another key effect in this region. Photons that climb out of the deep gravitational potential well near the black hole lose energy as measured by distant observers. This does not mean that the photons slow down, because in relativity, the speed of light remains constant in vacuum, but the energy and therefore the frequency of the photons change. A photon emitted with a given energy near the inner disk will be detected with a lower energy farther away, corresponding to a shift toward longer wavelengths. The amount of redshift depends on how deep in the potential well the photon originates and on the path it takes through spacetime. Combined with Doppler shifts due to the high orbital speeds of the emitting gas, this gravitational redshift broadens and skews spectral lines from the inner disk, especially strong features such as iron fluorescence lines. Observations of Cygnus X-1 show line profiles that extend over a wide range of energies in a way that is consistent with emission from radii close to the black hole, where both Doppler and gravitational shifts are significant. Light bending also affects the apparent brightness of different parts of the disk and corona as a function of viewing angle. Photons emitted upward from the disk surface on the side moving toward the observer can be both boosted in energy by Doppler effects and focused toward the line of sight by gravitational lensing, making that region appear brighter. On the receding side, photons are redshifted and may be bent away from the observer, making that region appear dimmer. This anisotropy contributes to the relativistic beaming pattern of the inner flow and introduces angle dependence into the observed emission. In spectra and light curves, these effects show up as subtle modulations that depend on the inclination of the system and on the distribution of emitting material in the inner accretion region. In an idealized image produced by tracing photon paths through a model of the spacetime around a spinning black hole, the black hole appears not as a solid surface, but as a dark silhouette against the brighter background of the disk and corona. This silhouette corresponds to the shadow cast by the event horizon and the photon orbit region, where light rays that would otherwise reach the observer are instead captured or deflected away. Around this shadow, the lensed image of the disk forms a distorted ring, and a series of arcs with the innermost bright structures tracing the last visible orbits of gas and the photon paths that skirt the unstable photon orbit. Although Cygnus X-1 is too distant and too small on the sky for current telescopes to resolve such fine details directly, the same principles govern how its inner regions would appear if they could be imaged at extremely high resolution. Instead of direct images, information about the light bending and redshift comes indirectly through spectral shapes, timing behavior and polarization. Polarization measurements in particular can be sensitive to the geometry of scattering and the orientation of magnetic fields in the inner flow, and they can be altered by parallel transport of polarization vectors along curved photon paths in strong gravity. Future and current X-ray polarimetry missions aim to use such data to refine models of the geometry and spacetime around black holes like that in Cygnus X-1. The interplay between light-bending gravitational redshift and Doppler effects therefore determines how radiation from the inner disk and corona is redistributed in direction and energy before it arrives at distant detectors. By comparing detailed general relativistic models of photon propagation in a spinning black hole, spacetime with the observed spectra and variability of Cygnus X-1, astronomers extract information about the black hole spin, the inclination of the disk, and the location and extent of the emitting regions in the strong gravity zone immediately outside the event horizon. Just outside the event horizon of the black hole in Cygnus X-1, the behavior of infalling matter changes from a slow inward drift to a rapid plunge. gas that has moved through the inner disk and crossed the innermost stable circular orbit, no longer has a family of stable circular paths available. Instead, it follows trajectories dictated by the curved space-time, in which radial motion grows quickly, and the distance to the event horizon shrinks on a short timescale, measured along the path of the infalling material. In this plunging region, the orbital component of the velocity remains large, but the radial component becomes comparable, and the flow accelerates toward the horizon, with little chance for further dissipation or exchange of angular momentum with material at larger radii. From the point of view of a freely falling parcel of gas, conditions change smoothly as it moves inward. The local gravitational field increases, tidal forces strengthen, and the radiation field from the disk and corona behind it shifts as the relative geometry evolves. But there is no abrupt physical boundary at the location that general relativity identifies as the event horizon. The horizon itself is defined mathematically as a null surface, in space-time a boundary beyond which all future-directed paths that light or matter can follow remain trapped and cannot reach distant observers. For an infalling world line that crosses this surface, local physics remains governed by the same laws that apply just outside, and nothing in the immediate neighbourhood signals that a one-way boundary has been passed. In contrast, for observers located far from the black hole and using coordinates that track time according to a distant clock, the picture looks very different. Photons emitted from gas approaching the horizon experience increasing gravitational redshift and time dilation. Each successive photon must climb out of a deeper potential well, and from a region where the comparison between proper time along the infalling trajectory and coordinate time at infinity becomes more extreme. As a result, the rate at which signals from the infalling gas arrive at a distant detector slows and their energies drop. In idealized calculations, emission from a small bright marker carried by the gas would appear to fade and stretch, in time never quite reaching the moment when the marker crosses the horizon as seen in these coordinates. In practice, real gas does not maintain a sharply defined bright surface during the plunge. It is optically thin in places, spreads out, and continues to interact with the radiation field and with itself. Emission from the plunging region becomes weaker, both because the available time for energy release shrinks in the proper frame, and because the strong redshift makes the escaping photons less energetic and more difficult to detect against other components. Most of the measurable radiation from accretion therefore comes from slightly larger radii, outside the point where the plunge begins. Even so, theoretical models that include the plunging region are important because some fraction of photons produced there can still escape and can contribute to the observed spectrum in subtle ways. The trajectories of these photons are strongly affected by the space-time curvature, so their contribution to line profiles and continua carries information about conditions extremely close to the horizon. The gas in the plunging region continues to feel tidal forces that act differently along radial, tangential, and vertical directions. For a stellar mass black hole of this mass at the radii just outside the horizon, the tidal gradients are strong but finite, and the plasma remains a continuous fluid on scales, large compared with the microscopic mean free path. Magnetic fields frozen into the gas are dragged inward with it, and any remaining stresses associated with these fields can continue to act until the flow crosses the horizon. Numerical simulations of magnetized accretion onto black holes show that magnetic stresses may not vanish completely at the innermost stable circular orbit, and can persist into the plunging zone, modestly modifying the simple picture in which torque drops abruptly to zero at that radius. However, the overall trend still holds that the efficiency of additional energy release inside this region is limited by the short proper time available before horizon crossing. From the point of view of global conservation laws, the energy and angular momentum carried by the plunging gas toward the horizon determine how the mass and spin of the black hole slowly change. As matter falls inward, its rest mass kinetic energy and internal energy become part of the total mass energy budget enclosed by the horizon, while its angular momentum contributes to the black hole spin. The rate at which these quantities are delivered is set by the accretion rate and by the distribution of specific angular momentum in the inner flow. Over long timescales, continuing accretion can spin the black hole up to high values, or if the angular momentum of the inflow differs in sign, can spin it down. In Cygnus X-1, modelling of the X-ray spectrum suggests that the spin is already large in the prograde sense, implying that much of the material that has fallen in over the system's history has carried angular momentum aligned with the disk rotation. The event horizon itself is not a surface with material properties in the usual sense. It does not radiate in the way a solid surface would, and there is no physical structure that could reflect or re-emit photons in the classical picture considered here. Instead, it is defined by the causal structure of spacetime as the boundary between regions where signals can eventually communicate with distant observers and regions where all future paths remain confined. For classical general relativity, this boundary is featureless apart from its size and shape, which are determined by the black hole mass and spin. The area and angular momentum of the horizon obey certain relationships that mirror thermodynamic laws, but the microscopic origin of these relationships lies outside the scope of direct astrophysical observation in systems like Cygnus X-1 and remains a subject of theoretical study. From an observational standpoint, the presence of the event horizon is inferred indirectly by the absence of any persistent solid-like surface emission, and by the ability of models with a one-way boundary to reproduce the spectral and timing properties of accreting black hole candidates more successfully than models in which accreted material must strike a surface and radiate additional energy. In the final approach to the horizon, the infalling plasma carries with it any remaining irregularities in density, magnetic field and composition. These inhomogeneities are effectively removed from causal contact with the outside universe once they cross the boundary, so their specific details cannot be recovered. What remains accessible to observation are the aggregate effects of all past infall episodes encoded in the macroscopic parameters of the black hole and in the radiation emitted before matter disappears from view. General relativity provides a consistent framework for describing this approach to and crossing of the event horizon, while also making clear that the interior region cannot be probed directly by signals that originate there and travel outward. Inside the event horizon of the black hole in Cygnus X-1, the description of spacetime given by general relativity continues formally, but the region is cut off from the rest of the universe in a causal sense. No signal particle or photon that crosses the horizon can later influence distant observers, because all possible future paths for matter and light within this region lead steadily towards smaller radii rather than back out to larger ones. In the language of general relativity, the radial coordinate that labels distance from the center behaves inside the horizon in a way that resembles a time direction more than an ordinary spatial direction. For any freely falling object, the sequence of decreasing radii plays the role of a one-way progression, and no physical process can halt or reverse this inward advance once the horizon has been crossed. The interior structure predicted by classical general relativity depends on the idealized properties assigned to the black hole. In the simplest non-rotating model, the solution describes a spherically symmetric spacetime in which the event horizon encloses a central region where the curvature of spacetime grows without bound. This central location is referred to as a singularity, not because it is a point of ordinary matter with well-defined properties, but because the mathematical description of spacetime itself ceases to be well-defined there. Tidal forces which measure how strongly gravity acts differently on nearby points increase as the singular region is approached. For an infalling observer, the proper time from crossing the horizon to encountering the zone where curvature becomes extremely large is finite, and for a black hole of a few tens of solar masses quite short, compared with many astrophysical timescales, although still long compared with the microphysical timescales of individual particles and fields. For a rotating black hole described by the Kerr family of solutions, the internal structure in the exact mathematical model contains additional features such as an inner horizon and a more extended singular structure. In these solutions, the geometry allows more complicated patterns of geodesics, including trajectories that in principle might avoid the singularity for some time, or pass through regions where the radial and angular coordinates behave in non-intuitive ways. However, many theoretical studies indicate that these inner horizons are likely to be unstable when realistic perturbations and infalling matter are included. Small amounts of radiation or matter falling into the black hole can be strongly amplified as they approach the inner horizon, leading to very large effective curvatures that are expected to destroy the idealized internal structures of the exact solution. In practice, this suggests that the extended internal features of the rotating solution may collapse into a region where the classical theory predicts very high curvature, again signaling a breakdown of the description rather than a smooth, well-behaved environment. It is important to emphasize that none of these interior regions are accessible to observation in systems like Cygnus X-1. All information about the mass spin and environment of the black hole comes from radiation emitted outside the horizon, where matter in the disk corona and jets interacts with the strong but still externally observable gravitational field. The no-hair theorems of general relativity, which apply in idealized settings, state that the exterior gravitational field of an isolated settled black hole is fully characterized by a small set of parameters such as mass spin and electric charge, regardless of the detailed distribution of matter that originally collapsed to form it. In astrophysical context, electric charge is expected to be negligible, so the external geometry is described by mass and spin alone. This means that as far as the external spacetime is concerned, many different possible internal histories of collapse and accretion lead to the same exterior gravitational field and the radiation produced in the accretion flow senses. Only these global parameters, not the detailed arrangement of matter once it has passed inside the horizon. Material that falls through the horizon from the accretion disk carries energy, angular momentum, and any embedded magnetic fields into the interior. In the classical picture, these quantities contribute to the total mass and spin of the black hole as measured from outside, but their individual identities are lost as they approach the region where curvature becomes very large. The equations of general relativity can be followed to the point where the singular behavior appears, but beyond that they provide no further prediction. This signals not an internal inconsistency in the theory at low curvature, but a limit to its domain of applicability in regimes where quantum effects of gravity are expected to matter. Many proposed theories of quantum gravity aim to replace the classical singularity with a more complete description, but at present no single framework has been confirmed observationally, and detailed pictures of the interior that go beyond the classical singularity remain speculative. In the absence of direct observational access, astrophysical studies of black hole interiors rely on indirect constraints. One such constraint comes from the lack of evidence for a solid surface in accreting black hole candidates. If the compact object in Cygnus X-1 had a surface, rather than an event horizon gas falling onto it, would inevitably crash into that surface and release additional energy, which would likely appear as persistent emission with certain characteristic properties. Models that incorporate such a surface often predict spectral components that are not seen, or energy budgets that do not match the observed luminosities and variability patterns. By contrast, models with a horizon in which energy can disappear from view once matter crosses the boundary match the data more consistently when realistic accretion structures and radiative processes are included. This supports the interpretation that the compact object in the system is a black hole with an event horizon, as described by general relativity, but it does not reveal the details of the interior geometry beyond that horizon. The causal separation enforced by the event horizon also affects how initial conditions for the interior are chosen in theoretical work. Any perturbations or irregularities inside the horizon cannot communicate outward, so for external observers, the only relevant information is encoded in the horizon scale parameters. Internally, the evolution of matter and fields continues according to the local equations, until the singular region is reached where the classical description stops. The interior can be thought of in this limited sense as a region whose influence on the outside is compressed into the macroscopic parameters of the black hole and the boundary conditions at the horizon. In the context of Cygnus X-1, this means that while the accretion flow disk corona and jets provide detailed observable laboratories of high-energy astrophysics and strong gravity, the domain inside the horizon remains described only by the extrapolation of general relativity and by general principles such as conservation of mass and angular momentum, with the detailed microscopic structure still unknown wherever the classical theory predicts a singular behavior.